welcome to the second session of the Hyperloop seminars of this semester. Today we have two interesting talks of one focus project, research project that EuroTube is conducting together with universities of Bolzano, ETH Zurich, TU Eindhoven, and TU Delft. The first speaker of the day is Ishaan Kaushal, who is representing the Free University of Bolzano, and he will be giving us more detail about his work on this joint project both speakers are doing today. To give a bit of context, Ishaan is doing a postdoctoral research study at the University of Bolzano, and he also conducted his PhD on LCA on sustainability in the Indian Institute of Science in Bangalore. The name of the talk today will be a comparative life cycle assessment on smart model factories. Basically, he's going to look into how such a construction plan can be realized with 3 different materials. So without further ado, Ishaan, I would leave the floor to you. And thank you very much for joining.
Yeah, thanks, Daniel. And thank you all the organizers for this interesting invitation. And now I'll share my screen.
Great.
Just let me know if you can see it.
We can see your screen.
Okay, great.
You can switch to full
presentation
screen
mode.
Exactly.
Yeah.
Excellent.
Sorry. Yeah, okay. So I think my screen is now.
Yeah, we cannot see it. We can see
okay,
it.
Great. So right now, so I'm Ishaan, and thank you for getting me to talk about our project. And currently, I'm a postdoctoral research associate at Free University of Bolzano. And just to give you a little bit brief about the project is about a smart mobile factory for infrastructure projects. And we are partnering with ETH Zurich, Univizi, and TU Delft and TU Eindhoven with EuroTube on this project. And the topic which I'm going to present today is about a comparative lifecycle assessment study for selecting the most sustainable SMF design. So I will take you through a little bit of introduction to the project, and then how did we reach those three designs, and then how we used LCA to come up with one of the most sustainable designs for this idea. So the project is about how is seeking to transform the execution of complex infrastructure projects. And it's basically the idea is to move towards technologically integrated processes away from traditional supply chain methods. And the idea is, we have to do a more economic and environmental friendly delivery of infrastructure projects with, progress in digitalization and industrialization. So bringing something like from borrowing things from, how automation is in manufacturing into construction side. And specifically in the case of linear infrastructure construction projects like Hyperloop, which is of our interest, where the construction site needs to move as the construction progresses. So the centralized manufacturing idea, can create more higher environmental impacts and may not be very efficient. So the main objective of the project is to conceptualize, design, and develop a prototype of a smart mobile factory used to sustainably complete the construction of linear infrastructure projects. Why do we need something like a smart mobile factory? Basically, a SMF, I'll call it, for a project like this. So one thing is the localized production for linear projects. So SMFs can be relocated along the project's route, enabling on-site production at various stages, and reduction in lead times. By positioning SMFs closer to the construction sites, production lead times are minimized and just-in-time production can be done. Improved cost and resource efficiency. So prefabricated components are produced closer to where they are needed, and this cuts not just the cost, but also minimizes the environmental footprint of the project. Scalability and modularity. SMFs can be scaled because we are making them modular in a sense and movable. So they can be scaled and relocated to match the project's current stage and needs. And this reduces basically the idle factory capacity and optimizes resource use over time. And then mobile factories allow for a fast assembly and disassembly, mobility and flexibility, modification of production capacities and functionalities according to conditions on site. So that's the broad idea. Why would we thought of getting something like a smart mobile factory for this for the Hyperloop project. Based on this project brief, we developed some requirements and concepts for the SMF design because we wanted to have a smart mobile factory design. And the major requirements which came out of our exercises were, first thing was ease of assembly and disassembly of the factory, the scalability and reconfigurability of the factory, design for longevity because you would want to use it for a longer number of cycles, and then reduction of carbon footprint of the factory designs and operations, and then minimizing logistics and interlogistics efforts of the factory. There was a whole exercise which was done, and how based on these requirements we came up with finally with these three smart mobile factory designs. So the first is a concrete based variant, and the other is a wood based version, and third is a pneumatic, more like an inflatable structure. So three variants, and these SMF variants had been conceptualized in the context of a Hyperloop track construction between Zurich and Geneva. That's the case we had created for this. And the study which I'm going to present now is, it takes into this consideration these three versions and of basically three concepts, and then perform a life cycle assessment to come up with which of these three performs the best in terms of environmental performance. So basically the research question which I have addressed here is which of the proposed smart mobile factory concepts is the most environmentally sustainable. Now, a little bit introduction to the LCA, because LCA is a method which we have used to calculate the environmental impacts. So LCA, some of you are familiar, and those of who are not, basically it talks about calculating environmental impact of a product, process, and services, and it takes into a whole life cycle perspective into account. And it has basically 4 steps. It starts from a goal and scope definition, then where you define basically the aim and the boundaries, and then you talk about inventory analysis, which is like a data phase of the LCA where you collect data, and then the impact assessment. Impact assessment is a place where all the data, how those material consumptions, energy consumptions, and emissions are translated into environmental impact categories, and then the interpretation. That would depend on the user. Are you a product developer? Are you somebody who's providing services? Your policy, all sorts of things, marketing, etc. So now so the potential construction of a Hyperloop transportation system between Zurich and Geneva was taken as a reference project for which the parts will be made by the SMF. That's the reference for this study. And the goal of the study is to analyze and compare environmental impact of 3 SMF variants, considering the Hyperloop infrastructure construction between Zurich and Geneva. So the system boundaries for this study, though this work was done almost a year back, and now we have progressed further, and there have been more findings, but as it is based on a paper which we presented, so I would take you through how what was the earlier idea was to move the SMF every 15 kilometers, because the total distance bit of the so basically we chose a functional unit which was defined as a distance of the Hyperloop infrastructure from Zurich to Geneva, resulting in 245 kilometers. Then the distance was modeled as a movement of the SMF from first location to the 17th location, because we were taking it as every 15 kilometer we wanted to move the SMF. That was the idea at that time, which has changed. And in the next presentation, my colleague Jianxiang will take you through that. The system boundaries, materials for making the SMF. So in this, we considered the material which we take to make to construct the SMF, the Smart Mobile Factory, the transportation of the SMF during the construction of the project. So we are taking here 17 different locations. So every time the 15-kilometer distance gets completed, we move the SMF from that to the next location. And then the assembly and disassembly cycles of the SMF. So every time you move it to a new place, you have to dismantle it, and then you have to reassemble it at the new location. Specific manufacturing machines and equipment were not considered in this analysis, because essentially they would be similar in all three versions. And this was more about selecting the version which suits our our needs in terms of environmental sustainability. So now, after this, lifecycle inventory data was collected, and as this was in the design phase of this SMF, so we had some data which was collected from the BIM models of these designs of these three SMF variants, because so we have had the BIM models of these three versions, and also through the data sheets of the materials and components. So from there, we collected the material related data, the dimensions, and how much material goes into making these SMFs. The assembly and disassembly durations and associated power consumption were estimated in focus group sessions composed of 5 researchers from Eurotive Foundation, University of Bolzano, and ETH Zurich, in which we discussed about assembly and disassembly durations. Reuse cycles for wood, concrete, and pneumatic variants were estimated to a maximum of 25, 80, and 100 cycles respectively. The IDMAT database was used to complete the modeling phase, and the processes were modeled in OpenLCA software. It's an open source tool for doing lifecycle assessments. Then basically the third phase, the lifecycle impact assessment phase. So here, whatever data we have collected, whatever material inventory we have to now translate into a limited number of environmental impact categories. And this is done through some characterization factors. And there are different lifecycle impact assessment methods. And what we have used is a recipe 2016 hierarchist. And basically the impact categories chosen were climate change and human non-carcinogenic toxicity. Based on all of this study, so we basically calculated these things. So the environmental impact scores were calculated for each of these three variants. So the blue one is concrete, the red one is pneumatic, and the green one is for the wood. And we can see the concrete is the highest emitter in both the impact categories. For the left side is a global warming, and the right side is a human non-carcinogenic toxicity. And the pneumatic based is the lowest impact in terms of both global warming and human non-carcinogenic toxicity. Also, like considering global warming, the pneumatic based SMF shows around you can see like 1/3 of the concrete based SMF and around half of the wood based SMF. And for the toxicity, the pneumatic based SMF is about half of the concrete, and almost equivalent to the wood. And based on this, we can say, okay, so now the pneumatic version is a better one in our case, and which was further used. And then the component-wise analysis was also done, because there were different components involved in making these smart mobile factories. So for concrete, we can see like the foundation, the prefabricated concrete material, and the transportation is the lead cause. For pneumatic, the concrete foundation and transportation are the major impact impact causing elements. For the wood, also concrete foundation, transportation, and the pillars, beam, and truss are the major ones. So basically the concrete foundation is same in all three versions, because the foundation has to takes a lot of load of heavy machinery, and we can say that overall we can say that concrete foundation and transportation have quite a high impact, and we can basically, the idea is to use such information to redesign and to improve the designs further. So the results reinforce the idea of introducing modular, adjustable, and movable factories to improve environmental sustainability, particularly in this case, global warming and human toxicity potential. The pneumatic variant emerged as the most sustainable option from both the environmental impact category perspectives. A key contributor to emissions in all three variants was production and transportation of prefabricated concrete floor modules. It's important to consider environmental sustainability of factories at the design stage, because whatever we say we we design today is going to impact the future, whatever the project duration is. So also having such decisions at design stage always is a good idea, because we can do a lot more at design stage rather than at the later stages of the project execution. So replacing the prefabricated concrete modules with alternative materials or lighter concrete modules is something which can be done, and which we further, like our team has tried to create different kinds of new kinds of concrete floor modules which are lighter, and they're testing the strength, etc. Also use of, let's say if we are going with a concrete variant, so inflatable roofs can be something which can be added to that, and that can reduce the amount of and the quantity of steel required. For the wood-based SMF variant, developing advanced and durable joints could help increase its longevity, thereby enhancing its overall sustainability. So there is something for all the versions to improve, but overall we can do good with the inflatable one, the pneumatic one, and that's the one which we had chosen for our further research. Conclusions and outlook. So overall, the analysis underscores the importance of considering both material choice and design in striving for more sustainable practices, industrial practices. Also, the work highlighted the contribution of SMF variants in total and component-wise to the environmental impact. The analysis revealed that the pneumatic-based SMF variant outperformed the wood and concrete versions. And the performance gap between pneumatic and wood was narrower compared to the concrete one. Also, we had a previous analysis where the pneumatic version was also the most cost effective. So both economically and environmentally, we can say we have the pneumatic version is better performing. And in the future, we will be performing further research activities to expand the analysis and include operations and other supply chain related impacts as well in these calculations. And in the more research in the future, the SMFs will also be compared with the traditional centralized factory approach, which I have already done and will be presenting next month, and which was not part of this research paper. And because the transportation showed to have one of the most negative impacts on environmental sustainability. And finally, this is the work which I'm presenting right now. You can access it. It's in the proceedings of APMS, which is a conference on advances in production management systems. This year, last month, we have presented this paper there. I will put out a link, and maybe you can have a look at this work as well, where a lot of things which I have talked about are done in detail. And so I think that's all. That's all from my side, and thank you all. And probably you can write to me, or you can also look at the project page and have a look at our partners, different people doing different things, and maybe if you're interested in anything, you can write to us, and we can have a chat later also. So thank you.
Perfect. Thank you very much for your presentation. There's already a few questions pouring in, so we'll start right into that.
Okay.
The first question that I want to highlight is the type of wood chosen also depends on the CO2 emissions. For example, if you take wood that has been replanted, it would theoretically emit 0 emissions. How far would this aspect change the LCA that you conducted?
Yeah, it can change, right? Because right now, if the wood is what we have taken is mostly the one which is available in the market, which comes to the market, and any industrial grade wood. Of course, we can talk about a lot about replanted things, but ultimately, it's we are going to make things with whatever is available in the market, and the analysis done on that actually, and rather than not on a specific case of course uh, there can be cases where we can have a wood from the sources which are more sustainable. Yes, I agree.
Okay. Yeah, but you've taken the market value, basically
Yes,
what's
yes.
currently and not any
Yeah,
sustainable
yeah,
water. So yeah,
yeah.
I think that's what the question really wants. Yeah. Based on the lifecycle assessment results, we see that pneumatic structures have a lot of potential. How can the industry make use of these results? In other words, is there something that can be patented for commercial use? If yes, what?
Yeah, so right now, because we are working with Eurotube Foundation, and most of the things, whatever we have done, are out in the public space. And I think the idea is there is a lot of exactly for especially for mobile factories, there's a lot of potential with the pneumatic ones, and not just for the construction, but for many uses of mobile factories. There's a lot of potential even in the areas of even in the areas of training, research, and a lot of other things. So yes, I don't have an exact answer on about the patent situation right now, but yeah, I think it's a good idea. I think we can actually think of doing something like that in this direction. Yes.
Then the next question is, how did you choose exactly those materials that you compared? What was the ideas? What was the prerequisites for that, the requirements?
So initially, so there were basically the idea was firstly to create based on the project brief. We had some sessions on how to generate basically the requirements for the design. So people use something like an axiomatic design to first to come up with various requirements, and then how those requirements will be fulfilled. And then for fulfilling those requirements, different material choices were taken, and then finally, some combinations of those material choices were then finally put together. And then so basically we started with a very divergent thinking, and then converging towards these things, taking more of a engineering design approach, uh, which any design task would take.
I'm right, yeah. And the last question for now, did you take into account that certain materials that might have less of a global warming potential need to be renewed more often or less often? Is that an effect? I think for infrastructure like a tube, it might be. For mobile factories, maybe not.
Yeah, so if I understood it correctly, so the question is about materials
So
that
yeah, and the renewal cycle, if you need maybe concrete has like a longer
yeah,
time and wood
yeah.
maybe a shorter
So
time.
yes. So we have considered the cycles, how many cycles these things can be used. Yes, and for that's why because for the wood the number of cycles were less, but then there was a suggestion that using some kinds of joints may increase the longevity, may increase the reusable number of cycles, and that's where also then the pneumatic version actually uh, uh, tend to fare better than other versions, where you have more options of where it has a longer lifetime as compared to the other versions. Plus, even replacing reusing and replacing something is quite easier compared to other versions. So yes, in a sense, yes, we have considered that. Yes.
Okay, great. And I'll hand over. Thank you again for your talk, and I'll hand over to Daniel again for the introduction of our next speaker. Thanks.
Thank you.
Thanks a lot, Ishaan, for the interesting talk. And with
Yeah.
this said, would then hand over the word to you, Jianxiang. Thanks for joining us. Well, Jianxiang will be presenting us about the same project, a more global view on how many relocations are actually needed to lower the carbon emissions in such smart mobile factories. So with this said, Jianxiang, we would leave the floor to you, and we are also looking forward to your results.
Thank you, Daniel.
We can see the presentation.
Yeah, I know. But, kind of. Okay. Is that all right?
That's great.
Okay, thank you, Daniel. Hello everyone, I'm Jianxiang from Chair of Sustainable Construction, led by Professor Jianxiang Ma. And I'm currently the third-year PhD student who is working on the basically life cycle assessment part of the smart mobile factory for infrastructure project together with Ishaan. So we know that for infrastructure construction, we have main three challenges. I think the first one is like sometimes we have delayed delivery due to like the massive production amount for linear infrastructure project. And also due to the delayed delivery, sometimes we would suffer from budget overrun. And also, and also due to the multiple thing here. A, B, C. And due to the length of the linear infrastructure, we need to somehow transport the material and also the prefabricated component maybe from very far away, and that may lead to very high logistic emissions. And here I just want to give a very high level structure of the smart mobile factory for infrastructure project. So basically, we have three research packages. In the first place, Ishaan's group, they would design different variations of smart mobile factory that could be relocated. And those factories are used to supply our innovative Hyperloop infrastructure. And the Hyperloop infrastructure would be studied as a case study to estimate the performance of the designed smart mobile factory. And at the same time, we have digital twin developed for the mobile factory, which utilize the cutting edge technology such as semantic design and also integrate with IoT sensors, so that we could collect real-time data in the field in the smart mobile factory and to calculate the cost and also the carbon emissions with higher accuracy. And my job is to utilize the functionality provided by both smart mobile factory and the digital twin to calculate the dynamic life cycle assessment of the construction process of the Hyperloop infrastructure and also the logistic involved in the construction phase. So we know that for the construction of linear infrastructures, we need to basically move the transport the element from the prefabrication mobile factory, as well as we need to transport the material from the suppliers to the mobile factory. So based on current EuroTube design, the main structure is made of concrete, and that this kind of material has a really good benefit we can utilize. It's like it is like the location of the suppliers, the mainstream material reinforcement, cement, and the aggregate is kind of everywhere. So that means that those three material is local material. So based on this this kind of scenario, we would know that it is logic to transport the mobile factory instead of transport the very heavy prefabricated elements, so that we could reduce the carbon emissions. Because whenever we move the factory, we could find the local suppliers for the material we need to produce the concrete prefabricated element. Okay. So that the question is like how many relocations we need to have a efficient carbon reduction. Here is the life cycle assessment system boundary we considered. I think Ethan has explained this part thoroughly in his presentation. So here we would go very fast. So the first part would be inbound transportations. Basically, is the material is the transportation associated from material to the smart mobile factory. The second one would be the outbound transportation that equals to the transport emission from the transportation of the prefabricated elements from the mobile factory to the construction site. And the third is the carbon emission induced by the relocation of the factory. That includes the transportation of the factory itself and the factory reconfiguration process. It concludes set preparation for the deployment of the mobile factory and the assembly and disassembly process of the factory itself. And in the end, we would restore the set to back to the initial condition. And therefore, as I introduced, we could split this problem into two-stage optimization, because the three main materials could be treated as the local material. So the first stage model would minimize the carbon emission from outbound transportation as well as the factory relocations. Here we introduce three binary decision variable in our optimization model. The first one would be the outbound transportation decision variable, which would match the supply from the factory to the construction site. And based on this decision variable, we could derive the second decision variable to represent the selection of the selection of the positions to deploy our mobile factory, and it will be represented by Y. And based on those two variables, we would have the third binary decision variable that links the selected locations for the mobile factory, so that we could estimate the carbon emission from the transportation of the mobile factory. And in this stage, we would minimize the carbon emission from outbound transportation and factory relocations. And we would have the factory deployment set, F prime. And also we would know the outbound supply chain represented, I think, here in the green line. And in the second stage, we need to locate the material suppliers for the selected locations for the mobile factory with the lowest transportation carbon emissions. And here we can see like we have the factory selection F prime, and what we have to do, what we need to do is just use another binary decision variable to find the suppliers with the basically like shortest distance. So in this stage, we minimize the carbon emission from the inbound transportation. We determined the material supply chain, and we finally we could calculate the overall carbon emissions from the logistic. And the implementation framework of the proposed two-stage optimization model is in the first place. We have the input data from the bill of materials, and we would know the location information of the candidate locations to deploy our smart mobile factory. And those information would be pre-processed by the Brightway for the life cycle assessment calculation, and also using the GeoPandas to calculate the transportation distance between the suppliers and the materials. And in the third stage, we would feed those information into the mathematical optimization package, which is named PyOmo and solved by the CBC solver. And in the end, we would compare the optimized scenarios for different relocation numbers and, of course, the fixed factory relocation scenario. So here's the case study we use. That is we assume the construction line would be from Zurich to Geneva, which is 248 kilometers. And for the infrastructure weight, it's 6,269 tons per kilometer. And the weight of the smart mobile factory, here we use the pneumatic version, which is very lightweight, and it also includes the equipment we need during the prefabrication process of the component, and also those are the carbon emission indicators for the transportation. And we have the results for the studied scenario. And we could see that we kind of have the optimal, which is like 17 relocations. And we could see that the factory reconfiguration process and also the transportation process of the factory is really small. The contribution of the transportation for those two are really small, and the average of the overall carbon emissions is around, I think, 30. It is around 3,700 ton of CO2 for 1 kilometer of construction of the Eurotube. And here we can see that those are the transportation distance for different relocations. The first one, I think, is for 4 relocation. The middle one is 6 relocation, and the last one is 8 relocations. And we can see that as the relocation increases, the main reduction is thanks to the transportation distance reduction of the prefabrication material, that is the outbound transportation. And for different relocation, for different locations of the mobile factory, the transportation distance of those three local materials are kind of varies, but only a little bit. And when we and it corresponding to the carbon emission from the material supplier that is the inbound transportation. It varies, but not a lot. So we could see that based on this study, the main reduction is due to the reduced transportation distance of the outbound transportation, that is the transportation of the prefabrication component. And we see that when the relocation numbers exceed 6, it varies. Sometimes it goes down, sometimes it goes up, and we cannot achieve a huge reduction by increasing the relocation numbers. So we suggest that for this case study, 4 to 6 relocation would be sufficient for when we operating the smart mobile factory. So the conclusion is the first one is using mobile prefabrication factory to supply large linear infrastructure can greatly reduce the overall transportation carbon emissions. And as the relocation number increase, the incremental carbon reduction decrease. So we propose 4 to 6 relocations. And the current work is we are conducting a sensitivity analysis based on different scenarios. That means we would generate the like different lengths of the Eurotube infrastructure, and we would somehow modify the locations of the suppliers. And based on that, we would conduct our sensitivity analysis to see whether the recommendation is like a 4 to 6 relocation. It's like 50. It's like every 50 kilometer we could relocate the mobile factory. So we would somehow test whether this conclusion could be applied into different scenarios. And at the same time, we conduct a cost analysis for economic feasibility evaluation of different relocation plans. And that marks the end of the presentation. And thanks, everyone. Thank you for staying late with me. Any questions?
Right. Thank you very much for your presentation. I was saying one, there's now 2. There might be more. So the first question is asking, how did you characterize the case you compared it to? I think it's mentioning no mobile factory. Is literature available for such a case where you have no mobile factory? Hyperloop seems to be a kind of outlier for those infrastructure projects maybe, but maybe wind turbines have similar transportation constraints as Hyperloop tubes. How did you compare your mobile factory case compared to a no mobile factory case?
Yeah, that one is like basically everything is the same. We just deploy the smart mobile factory once, and we don't move it. So that means we have 19 candidates, and we select the best one, and no movement of the mobile factory at all. So
so it's not one factory somewhere in the country, but it's one mobile factory, but stationary basically.
Yes, because like if we put the mobile factory like at the end or at the start of the infrastructure, it would kind of have a really high emission. So this scenario, I didn't show the map, but basically it's kind of lying in the middle of the infrastructure line. So it's kind of a really good. That would be the best case somehow for the stationed scenario. It's not we modify that so that we could have a good result.
Yeah, very nice idea though. Yeah, I like it. I like the comparative case. And then there's the next question. How easy is it to adapt this model or tool to other Hyperloop routes? and it would be a great idea to do a usable tool out of the study to apply it to other projects if you can.
Yes, so currently I think I developed the code somehow could be modified easily to I think other Hyperloop variants. And I think after we have finished the sensitivity analysis, we would open source that the code, the script, so that people just input the weight of your Hyperloop design and the smart mobile factory. And considering the emission factor for different country would be different, it's just replace those factors in my script. Then I think import the locations candidates we selected in I think like a JSON format. Then run the code, then it would automatically give the result. I think
for others as well.
Yeah, for other variants of Hyperloop, like maybe we would need a steel tube or something like that.
There's more questions coming in. The next question is, how easy is it to change in your model or tool the material parameters using steel, for example? Maybe that implies other needs for logistics and other thicknesses of the material, other weights. How would you be able to change this, or how quickly would it be able to change the material? Can you just select the material in your tool, or do you need to have different parameters?
I think for the code it will be easy for the steel tube, but I think the problem is like whether we have a local supplier like concrete, so that we could produce. We could basically order the tube, the basic steel tube from the supplier, so that we could reduce the carbon emission. And for the code is very simple. We could locate the suppliers in Google or whatever, and just feed that because my code would read the code, the GeoJSON data form directly, and we just run the code. It would give us the result, because when it would only need to change the weight, because the transportation is kind of related to the weight and also the method. But for Eurotube, for such infrastructure, we always need a very large truck. So the emission factor is kind of fixed. We cannot alter to like smaller one or something like that.
Yeah. Is there, I don't know if you know, but to my knowledge, I think it's not possible to manufacture steel tubes in like 4-meter diameter with a mobile factory. But I think you're more versed in concrete, right?
Yes.
For concrete, there's a possibility to have the mobile factories, but for steel, I haven't seen. I think I've only heard about steel mobile factories for like maybe just up until 1-meter diameter steel tubes and not 4-meter diameter. I see other people nodding. Okay.
Yes, I think for steel version, it's like, do we really need a smart mobile factory? It's like an intermediate point. I don't think, especially like here in Europe, we know that there are not a lot of suppliers who can really manufacture such tube required for Hyperloop. So I don't think for tube version we do really need smart mobile factory. But there's one thing, like the carbon emission from the steel version, the embodied emission is really high. So we need a holistic life cycle assessment for those two variants. And in that scenario, the transportation is like only 5%, or maybe even lower. So the transportation is not the concern; it's the material itself.
Yeah. Okay. I think that's all the questions for now. Thank you very much for your presentation. I'll hand over to Daniel again for telling us maybe what we hear next time.
Yes, thank you very much, Lucas. Thank you very much, Jianxiang, for the nice presentation. With this said, we can also announce the talk we have for coming Monday, 4th of November, same time, 6 to 7 CET. And this time we will be having in-depth explanation of colleagues of the University of Southampton, Jaime Renedo Anglada and Suleiman Shark, and also colleagues from Swissbook Technologies, Dario Bueno Vaques and Dennis Tudor, who are going to be talking about the design of a high-speed linear induction motors, more specifically how end effects can be reduced in this type of motors. So with this said, we also appreciate for everyone joining today, and I hope to see you also next week.